Hi, my name is Leonardo Crespo. This time I'm going to talk to you about the definition of target population of environments in India for wheat breeding. Let me start by mentioning that South Asia is an important region for wheat breeding at CIMMYT, where wheat is a staple food for almost 2 billion people, and it is grown in more than 40 million hectares. Out of those 40, 30 million are harvested in India alone, with an average yield of about 3.2 tons per hectare. The main testing site for CIMMYT in Mexico is in Ciudad-Obregon in northwestern Mexico. It's a place with a semi-arid climate, with water availability, favorable temperatures for growing wheat, irrigation infrastructure, and mechanized operations. These characteristics allow for the simulation of different selection environments where new lines are tested every year. We routinely simulate 6 selection environments, 2 in optimal conditions that differ in their planting system, 2 water stress environments for severe and intermediate drought, 2 heat stress conditions where plants are subject to late and early heat. A big advantage of this testing site is that it is possible to evaluate the materials for heat and drought stress, yield potential and stability in one single place. Environment classification at CIMMYT has been done since the 1940s, first restricted to Mexico, but later it was extended as soon as CIMMYT scope became global in the 1970s. In the 1980s, the concept of mega environment was formally defined to include socioeconomic traits. And by 1992, 12 mega environments had been conceived, 6 for spring wheat and 6 for winter wheat. With these various studies followed and demonstrated how Obregon selection environments correlate with such mega environments. This study follows on those previous findings by redefining mega environments in India to TPEs by using more information and additional analytical methods. For this, we use 16 years of grain yield data from the internationally distributed elite spring wheat yield trials, given 245 side year combinations for analysis. For the same period, we used meteorological variables from the NASA Power database, which was utilized to implement principal component analysis and hierarchical clustering to group all the locations where the trials were conducted. The grain yield of the data was analyzed to estimate variance components and calculate selection-related parameters. Also, we took 5 years of data generated from the selection environments and TPEs to conduct pedigree-based predictions with 3 different models. The first model was just the main effect of the lines and the environment. The second model was an extension of model 1 that includes the genotype by environment interaction. Model 3 was an extension of model 2 that includes the variables that separated the TPEs along with their interaction with the lines. From our analysis, we found that sites in India were grouped into 3 different TPEs. TPE 1 in the northwestern plain zone, which is an area with higher yield potential, and where normal maturity germplasm is required. Based on mega environment classification, this TPE would align to mega environment 1. TPE 2 in the northeastern plain zone, where heat stress is a factor and soil material is required. This TPE aligns with mega environment 5. The TPE 3 in the central and peninsular zone, where heat and drought stresses are the main factors, and early maturity material is required as well. This TPE has the characteristics of mega environment 2. The differentiation of the TPEs was more evident in the temperature patterns and some soil characteristics when we looked at the variables that were used to classify them. For instance, TPE 1 has the lowest minimum temperature, whereas TPE 2 and TPE 3 have higher temperatures, but different relative humidity, which is higher in TPE 2. As you know, higher temperatures with higher rates of relative humidity can cause the development of leaf diseases other than rust. In fact, one of the most important leaf diseases in TPE2 is spot blotch, which can cause significant grain yield losses. Similarly, given the lower average temperatures in TPE1, yellow rust is currently the most relevant disease in that area, even though rust as a group of wheat diseases occur in all wheat growing zones in India. In terms of soil characteristics, larger differences were observed in the percentage of available soil water capacity, which was lower in TPE3, possibly due to the larger fraction of coarse fragments. Large differences were also observed in the soil texture, for which TPE1 can be classified as a loam type, TP2 as a clay loam type, and TP3 as clay type of soil. Regarding the variance components from the combined analysis of the sites, we found that the size of the genotype by TPE variance was much smaller than that of the genotype by site within TPE. And the size of the genotypic variance was 19% of the genotype by site within TPE interaction. The heritability was 0.3 and the response to selection was 0.08. The size of the genotypic variance in each TPE was higher than the one of the combined analysis, and its size relative to the G by site interaction was up to 54%. The heritability was higher than 0.3, and the response to selection was higher than 0.11. These results indicate that greater gains can be achieved in the TPEs by targeting selections by TPE rather than without the subdivision of the TPEs. Across selection environments, the genotypic variance was substantially higher than the genotype by selection environment variance. If we compare the size of the genotypic variance relative to that of the across sites of the TPEs, we can see that it is about 3 times higher, and its relative size to each of the TPEs was between 1.4 and 3 times higher. The estimated response to selection across selection environments was 3 times higher than the one across the TPEs, whereas it was about 2 times higher than that of each of the TPEs. Disregarding selection intensity, the relative selection efficiency can be between 0.4 and 0.9. However, the selection intensity in the selection environments is higher than it is in the TPEs, given that many more lines can be tested in the selection environments. The results that we observed are largely because the heritability in the TPEs is lower than it is across the selection environments. Hence, greater gains in the TPEs can be achieved by improving their testing conditions, as well as increasing the selection intensity in the TPEs. For instance, we could say that we can test more lines at early stages in the TPEs. When applying the pedigree-based prediction models to assess the predictive ability of the selection environments, a large proportion of the total variance was accounted by the main effect of the environments. In fact, the proportion of the additive variance relative to the total of the prediction models for each selection environment was up to 8%, and the proportion or the PBT for the environments remained close to 90%. When the models did not include the information of the meteorological variables and their interaction with the genotype. In all cases, the PBT of the G by E was lower than 10%. And also, in all cases, the size of the additive variance was at least as big as the additive by environment variance in the models that included the genotype by environment interaction. In most cases, the environmental variance dropped significantly with the inclusion of the meteorological variables, which indicates that this information contains an explainable proportion of the environmental variance. The results from the pedigree-based predictions indicate that TPE1 is mainly associated with the selection environments called bed 5 irrigations and beds 2 irrigations. The selection environments that displayed higher association with the TPE2 were beds with 2 irrigations and beds with 5 irrigations and flat drought conditions, whereas beds with 5 irrigations, 2 irrigations, and late heat displayed higher association with TPE3. In agreement with previous findings, the inclusion of the G by E term in the prediction models and environmental covariables generally tends to increase the prediction accuracy of the models. Just as a final comment, we can say that Obregon permits to phenotypically evaluate grain yield in a more accurate way than it is in the target population of environments, given the characteristics that the site has, as I described before. We can also say that additional interventions in the TPEs besides increasing selection intensity and early testing can be made. For example, improving the trial conditions to increase the heritability in the TPEs. And generally, we can say with other data that has been published from CIMMYT, that higher selection intensity in selection environments has permitted a continuous genetic yield gain in target environments. With this, I would just like to finish my presentation and would like to thank you for your interest. Want also to acknowledge our funders that support the Bread with Breeding program at CIMMYT. Thank you very much.